It is, yeah. The Iron Man logo is glowing. Okay, remember what we did the last thing yesterday? Remember I bring across this horror movie where I introduced this one. Yeah? It is the horror movie called Integration. It's delta P. Now I'm going to give you another question, a slight twist to the question I last gave you, but it tests you on the same thing. It's a twist and it tests on something regarding momentum. So say this is 4 kg and this is 10 meters per second, and I exert a force, and the force goes like this. And this is 80, and this is 6. So find the change in momentum and find the final velocity of the object. Give it a try. Concept-wise, it's the same as before. What we did last lesson, which is the change in momentum is the what of the graph? Area under the graph, correct. Yep, excellent. So go ahead, find the change in momentum and find the final velocity. I think the area under the graph should be quite easy, even though the lines may not be that straight, but I think you can figure out that it's a triangle. So it's half base times height, which means that it is going to be 480, right? Okay, I'm just checking whether you're still alive. It's obviously 240, right? 240, okay, good, you're listening. 240, yep, 240 Newton seconds or kg meter per second. Why? Because it's force times time, or it's mass times velocity, which is kg times velocity. Both units are the same. Yeah, both units are the same. Now, final velocity, you just need to add the 240 to 40, and then you get 280, and then you just divide by 4, you get 70, right? I don't know. What's wrong? What's wrong? Something is wrong, yeah. Something is wrong. So you take 40, then you plus 240, then you divide by 4, then you get 70, oh? Again, sorry? Okay. It depends on what you take. Yes, correct. Because implicitly, I've already taken what direction to be positive? Left, yes, correct. Because I label the force as positive and it's acting this way. So what happened is that this should be negative 10. Be sensitive to direction. That's what I'm trying to bring out across for this example. So therefore, the change in momentum follow the system is always final minus initial. So the change in momentum is 240 equals to final momentum minus 40. So change in final momentum is 200. So the velocity is going to be 50 meters per second towards the left. Okay. Now, a higher order question is, if I were to ask you to draw, people don't usually like graphs. If I were to ask you to draw the momentum against time graph from 0 to 6 seconds, how will it look like? Now I need to give you another piece of information. Say it reaches the maximum at 3. How would the momentum against time graph look like? How would the momentum against time graph look like? I'll give you about 2-3 minutes to think about the shape. And after you know the shape, add in the values. Yeah, the shape first, then add in the values. Then you must think about what governs the shape. Is this word that starts with a G? What governs the shape? Like say for example, this is a straight line because something is constant. Gradient, correct. So then what governs the gradient? What determines the gradient of a momentum time graph? What is dp dt? F, exactly. So if the F varies in that way, how would my gradient change? Then if my gradient change in that way, how will my graph look like? Then once you get the shape, then you just need to shift up and down to the values. Yeah? Okay. So this is like the thinking process. Graph, shape and values. What determines the shape? Gradient. What determines the gradient? Look at it for quantity. So it starts off with minus 40. I hope you can recognize that. Like a hill. It's very interesting. What you're thinking of is exactly what I wanted to surface. Think carefully. Does a decreasing force means decreasing momentum? Decreasing, yeah. Does a decreasing force means decreasing momentum? If the amount that you save up every day decreases, does your saving increase or decrease? If your savings every day decreases, does your savings increase or decrease? Still increase, correct. So when the force decreases, so long as it doesn't get negative, the momentum should always be increasing. So there shouldn't be a correct. Careful. Remember we talked about that yesterday, that when velocity is zero, acceleration is zero, displacement is zero, that generalization. When the force decreases, the momentum must decrease. Wrong, huh? Wrong. Can? Yeah, wrong. Careful, be very careful about this kind of thing. F equals to dp dt. Somehow it must start off from here and end off over here, which is 200. Where does it cut? Does it cut at 3? Does it cut at 3? Are you able to determine where it cuts at 0? Cuts at 1. Why? Why? Okay, I just need you to answer me. Does it cut the x-axis at x at time equals to 3? No, no, it is not. It is not. It cuts before 3. But something happens at 3. What happens? The graph reaches its... What is maximum over here? Yes, correct. Maximum gradient. I want to see that. Why is it the maximum gradient? Because the gradient is the net force. So I want to see a few things. I want to see that the shape looks like this. I want to see indication that the maximum gradient is achieved at t equals to 3. And challenge question. Can you find the time where it hits zero momentum? Give it a try. Stretch a bit. Yeah? Can you find the time? No. This can't be the question. No. Denial. IB exam come out. No. This is bad question. Same. This is poorly set question. Find the time where the momentum goes to 0 using this graph over here. This is a straight line graph. One? You sure it's 1? I don't think it's 1. You need some working. One. Yeah. You see, when the momentum is 0, what can you say? It happens at some time over here, t. What can you say about the area over here? It is 40, correct. So how do you work that out? So say the gradient of this graph is going to be 80 divided by 3. So the line, the equation for this graph is f equals to 80 divided by 3 times t. Agree? Yeah, that's the equation for that graph, for that portion over here. So therefore, at time t, the area over here must be equals to 40. Therefore, using this graph over here, half times f times t, which is equals to half times 80 upon 3 times t must be equals to 40. Bang, bang, 40 over here, bang, bang. Then you got t equals to root 3, correct. Yep. So, first of all, you have to understand that the gradient, the area under this graph must be equal to 40 when this cuts 0. Why? Because it brings the momentum to 0. Yeah? Then the question is, how do you find this time? You have to use the gradient of this graph and then half times height times time to get the time. Cool? Okay. Yeah, it's not that hard. No? You mean the IB part or the... Cool? This part over here where you have to find the time is slightly above IB. I don't think, I've never seen IB questions that requires you to do that. But it is within syllabus. Yeah, it is not seen in IB, but it is definitely well within syllabus. Just that the math gets a little bit messy over there. Any questions before we move on to something that talks about the momentum of a system of particles? What happens when you have explosion? What happens when you have collisions? Yeah, something about momentum is very interesting. Any last questions? Before we go on to this thing called COM. Say you got two objects over here. This is force that A exerts on B. This is force that B exerts on A. Is this correct? Mathematically? Yes or no? Usually when Mr. Terence Chu asks you this kind of question, the answer is usually same. You see, this is how human minds works. Just because of 3 examples, same, whole life same. Just 3 examples. Correct or not? Ah, thank you, Hannah. Yes, negative. Why? Because it's equal and opposite. Correct. The opposite must be here. Okay? And multiply by time of both sides. Time, do you agree that the thing has changed? Just multiply by the time of the collision. Yeah? So what is F times time? Relate back to something you see over here. What is F times time? Change in momentum, correct. So therefore, if this is the force that A exerts on B, it's a change in momentum of B. And this is the change in momentum of A. And therefore, if you bring over change in momentum of B plus the change in momentum of A equals the change in momentum total, which is 0. So what does it say about the momentum of 2 particles that are colliding? That the total momentum of the system is conserved. Now this is really amazing. If you think about this, the premise on which this is built on is on Newton's 3rd law and Newton's 2nd law. This is 3rd law, this is 2nd law. This jump over here is 2nd law. This is 3rd law. Now, there is no other assumption that is built on. I didn't assume that energy must be conserved. I didn't assume that anything else must be conserved. So long as the 2 laws are true, it will always be true. And that's how powerful it is in any collisions, cars and cars. Human and human, I don't know why they collide, but human and human collide. It's kind of weird, but yeah. Whatever, particles and particles collide. By the way, the idea collision doesn't mean that they must touch. It can be electromagnetic interaction and goes like this. It can be 2 magnets, doesn't touch each other and go like this. It will always be true. Conservation of momentum always holds true. That's how powerful it is. Yeah? Based on these 2 laws, it came up with this. So let's apply this to see how it applies. But of course, some of you will be thinking what happens when relativity comes in. Yeah? Waiting for that. There's a relativity equivalent of conservation momentum. Yeah? But momentum must be conserved in different frames. That's the idea. Let's take a look, yeah? Yep.
Isn't true that light has momentum?
Okay. Yeah, we go. It's a very good question. It's a very good question. Light. Is light light? Is light? Does light have mass? Okay. The idea goes like this. Light carries energy, right? Energy has mass, right? So if you have mass, something with mass traveling at a certain speed, there's momentum. Yeah. If you model light as particles, entertain me just for 1 minute. And if you have this light particle of energy E equals to hf, it is known that the momentum of the particle is P equals to E upon C. So you take the energy of this light particle, which is hf upon c, that's gives you h upon lambda. So this is the momentum of the light particle. And this is not sci-fi. This is not sci-fi. This is exactly what scientists have been using solar sail. They launch a satellite, they open up a big sail, they catch the sunlight. The sunlight basically have a lot, billions and gazillion number of photons striking the solar sail, giving it momentum to move forward. So it is real, it is not, yeah. So in fact, if you want to find the force that a beam of light exerts on an object, you must take power divided by the speed of light. Now, you know how big this number is, no? Yes, correct. So to exert a 1 Newton force, this must be 3 times 10 to the power 8 watts. And if you don't know, this is enough to fry 2,000 chicken in 1 second. It's a lot of power. Just to give you another order of magnitude, this is probably 50 watts. It means that it can power 6 million light bulbs. The kind of energy you need to produce to have 1 Newton force. So we are talking about a big amount of power to generate a very small amount of force. That's why when you turn on the lights, you don't get pressed down. You switch on, cannot press down. You don't, yeah, because divided by speed of light. But if you were to have a very sensitive weighing scale, you turn on the lights, actually a bit, yeah, can? So it's actually, yes, back to your question. Does light have momentum? Yes, absolutely yes. Yep, can? Okay, but let me, since you asked this question, let me bring a thinking question for you to think about. We talk about light as a wave coming into a region and then it goes this way, right? It goes through this thing called refraction, yeah? Now, if light as a particle is correct, this model is correct, right? If you fire a gun into water, do you see the bullet twisting? You don't, you see the bullet going straight through and then you slow down and drop down. So why is it that the model of a light as a particle doesn't cause that refraction, but light as a wave, it does? Why? Why is it that these two models just doesn't seem to gel? You think about this, how to reconcile the two models? Okay, think about this. There is a reason why. You're going to find out. Just to stretch, give a question back in return. Think about this, light as a wave bends, but light as a particle, how come it bends? Cool? Light has volume or not? Light particle got volume or not? How does it look like? Light is particle, then you use another light to look at the light. How do you see the light? It's like, yeah, how do you see light? It's almost philosophical. How do you see light? You see, if this may sound a little bit TOK-ish. How do you understand an idea? How do you understand an idea? F equals to ma. You need another idea to operate on the idea. You need an idea to understand an idea. You cannot understand an idea in vacuum. To understand F equals to ma, you must have prior understanding of mass, acceleration, and force. And everything gets built up, you see. So you need to use an idea to understand an idea. But if you come back to this, how do you use light to understand light? Cannot fathom. Okay, so let's come back. Let's come back. Yeah. We got 15 minutes left. Okay, let's jump into the deep end of the pool. 4 meters per second. This is V. Let's give this 10 meters per second. This is 8 kg and this is 6 kg. After collision, this 6 kg mass move at a speed of 3 meters per second. This one moves with a speed of unknown. Okay? So I'm going to draw a table. This may look a little bit noobish, but have patience. It will be helpful in the end. So you got A, you got B, you got initial, you got final, you got total. No, it shouldn't be that way. It should be total here. Okay. What direction do you like to be positive? Right or left? Naturally, human beings always like the right side to be positive. Why? Because, why? Because when we write, the progress is always towards the right. Yes, correct. So mental models are mental models. English and a lot of languages is written from left to right. So our idea of progress is always from left to right. But the Chinese may have a very different way. Right to left is actually the system. Yeah, so yeah, naturally we go towards the right. So the initial momentum of this is 24. The final momentum of this is minus 18. Initial momentum of this is minus 80. This is unknown. Yeah. So the total momentum over here is going to be 56, and this is going to be 56. Yes, correct. So will you want to use this system and find for me the answer for the speed of B, the velocity of B? You'll find something weird, I think, because a pool, yeah, it's faster than, it's going towards the left and it's faster than 3 meters per second. Okay, poorly set question, but okay. I think I can salvage the situation if I were to put this at 6. Can otherwise you'll find that it's something weird will happen. This is minus 36 then. Is it going to be better? 20, yeah, correct. It's okay now. So, minus 36 plus 8 times V equals to minus 56. 8 times V is equals to minus 20. V is going to be equals to minus 2.5. So which means that, what does it mean? If the V is equals to minus 2.5, it means that it goes to minus 2.5. Minus 2.5, positive this direction, so it's going this way. Yeah. V is going this way, yes. That means that if I get a negative answer, it means that it points opposite. Okay. Cool. Now let's try a question and see whether it works for this one. So say this is, and this will invoke a certain interesting question over here. This is M, and you got a big truck over here, there's 3M, and this is V, and this is V. Find the final velocity of the wreckage. Okay, this is morbid. If the two vehicles are stuck after collision. Okay, it is quite morbid, but yeah. So you got a car traveling towards the right at speed V. You got a truck traveling towards the left at speed V as well, but mass 3m. The two of them get stuck together after collision. What does getting stuck together means? What does it tell you about the final velocity? Exactly, same. Unlikely that the car will pass through. So find the final velocity. And then I got an interesting question that you need to think about. Counterintuitive. You'll know later. So the final velocity is? Yeah. Set, but yeah. Any answers? V over 2. So it's minus V upon 2. Yeah, it is correct. Question number 1. Who is going to suffer more injury? The driver of the car or the driver of the truck? Car, right? I mean, common sense tells you it's car. Now, someone disagree, saying that by Newton's third law, and quote Newton, Newton's third law says that the force on the two objects are equal and opposite. And since they suffer the same equal and opposite force, why would the driver of the car suffer more injury? Why? The force is the one that causes injury, alright? Force is the one that causes injury. Then since the force is equal and opposite, why do they suffer different degrees of injury? More change in velocity. But okay, but how do you relate a change in velocity to the factor that caused injury, which is force? Yeah, change in velocity doesn't directly hurt you. It's the when. Alright? Impact. But Newton's third law says that it's like what? Newton's third law says that force is equal and opposite. So what's the problem? Where's that gap there? There must be a gap because we know that the person who's going to more likely to die is the driver of the truck of the car, not the driver of the truck. Two sets of forces. Which are the two sets of forces?
This is one of the car on the truck, and the truck acts on the car, but that's not the same force. Like those two are equal.
Yes.
But there's another one on the truck on the car, and the car on the truck, and those two are equal. But those four sets of forces are not the same.
Okay, you're almost there. Just that you missed out one very important component. That the force by the truck on the car and the car on the truck, they are the same. That is correct. They are the same. But that force is not equal to the force that the person experienced. Let me show you. Let me show you. You're almost there. I just wanted you to bring in the driver. Yeah, you're almost there. Let me show you. Let me show you the logic. F by car on truck must be equals to, in magnitude, we just talk about the magnitude, truck on car. Agreed? And we also agree that the mass of the car is smaller than the mass, this is car on truck. So it is the truck that experiences the force. So truck and car. No, unless it's a very heavy car. Some people can argue saying that it may be the President's United States. What's the name of the car for that? The Beast. Yeah, the Beast. The Beast is a 5-ton vehicle, by the way. Yeah, usually it's about 1 ton. It's a 5-ton vehicle, armor plated. So if it strikes a truck, the truck might die. The Beast. Acceleration equals to force divided by m. So you take the same force divided by a bigger mass. The acceleration of the truck is going to be smaller than the acceleration of the car. Like what you said just now, Shading, you said that the acceleration, the change in velocity is different. Because the acceleration of the truck is lesser than the acceleration of the car. Now this is the crucial step. The force experienced by the driver is equal to the mass of the driver times the acceleration experienced by the driver. Assuming that both drivers have the same mass, do you agree that mass of driver times A of truck is going to be smaller than mass of driver acceleration of car? Yes, correct. Because the truck is bigger, so the A is smaller. So the MA experienced by the driver is smaller. You can, okay, this is quite bad physics, but I can almost say that the force is distributed over a larger mass. Bad physics, but yeah, kind of. It's like force per unit mass is lesser. So the moral of the story is drive a truck. You survive. Hey, but if you got a truck that's quite cool, like the Tesla truck, you know, truck. But Tesla truck, look at that. It's very cool, okay? So it's not about the vehicle. If you got a cool enough truck, people will drive it. Yeah. Just like motorcycle, there are some billionaires who actually love motorcycles, and some motorcycles are really cool. Yeah. Can? So it's a very nice question that has some intricacies inside. Not a simple equal, same. Yeah, not the same. Yeah. Now, the last one is this thing, what we call the elastic collision. Yeah, elastic collision. Now, I'm going to write the derivation, and you just A, UA, UB, A, or probably instead of me deriving for you, you can try deriving for yourself. Do you agree that MAUA MBUB must be equals to MAVA plus MAMBVB? What's the principle based on which this equation is based on? Conservation of momentum, correct. This one? Conservation of energy or KE? KE, just KE alone, because it's only KE. I don't know whether the other energies are conserved, but KE. Now, using these two equations, can you derive this equation? Give it a try. Give it a try. Play with the... Let me help you a bit. Helpful, right? Very helpful, right? That's what happens. My students, so you got tips or not? Yeah. Got tips. The exam is going to be in English. Give it a try. See whether you can derive it. Just manipulation of equations, obviously. Obviously, manipulation of equations. Yeah. Try. Let's see how good your math is. Yeah, it's math. It's really math it out. Some factorization, if it helps. You need some factorization. You need some cancellation. Sure not? Sure. Whose is this media resource? How? Getting it? Got it? Good. Yeah, some cancellation here and there. Give it a try. See whether I can derive this. X squared minus y squared is equals to x plus y times x minus y, right? Yeah. Correct. You need to use that. Then you can strike off the top bottom, leaving this. Then you can get an answer. Can? I'd like you to think about, for those of you who have derived the expression, is there such thing called elastic collision in the real world? You got two billiard balls hitting each other. Is it elastic? No. In the physical world, whenever you can hear the collision, energy must have been converted. So hang on. But that means that there is no elastic collision in the world? Not in the world that we're more familiar with. How about subatomic world? Where you got protons colliding with protons? Possible? Yep. So elastic collision seldom happens in real life, as in the life that we have. It usually happens in subatomic particles, where there's no contact. Then some people will say, hey, proton and proton collide got sound or not? Then my question back to you is, what's the sound of a proton and proton collision? How does... Pong, ping. How does it sound like? Proton and electron collision. It's like, okay, interesting. Then the question is, what is sound? What is sound? Think about this, huh? What is sound? Yes, vibration of air molecules. So, yeah. So how does a proton-proton collision sound like? Think about this. We'll stop the recording today, but let's not stop the lesson.